Okay, so in section 13.2 and 13.3, we're going to be learning about something called a line integral. And the general idea is that recently we learned how to integrate over areas and volumes in these kind of 2D and 3D integrals that looked like this. So you could integrate over a 2D region like this, accounting for some function f, or you could integrate over a 3D surface. I don't know, let's do this one just for fun, where you would have some function f that you were adding up everywhere on that surface. Not pictured here. And now we want to think about something that isn't 2D or 3D, but is actually just running in one dimension. And those are curves and lines. So that's a curve C right there. It actually, let me make it more fun. That's a curve C. It lives in the XYZ coordinates. It doesn't go in a straight line that could easily be described as something that only moves in X, Y, or Z, but it doesn't take up space the same way a region or a volume does. It's a 1D object that just happens to stretch out in funny ways through 3D. You couldn't shade something in using this curve. And the way we're going to denote this kind of integral, which we'll call a line integral, over this type of object is over some curve C. We're still thinking about integrating some function f. And instead of using this dA for area or this dV for volume, we're going to use here a ds, where that just sort of stands for integrating over length. So we're going to integrate over a curve or line C, still a function of 3 variables, or 2, the z could be absent, that's fine, because the curve can move through 3D, so your function that you're evaluating on the curve can change with all 3 variables. And we're thinking about this with respect to curve length. So we integrated with respect to region area or region volume before, and now we're going to think about curve length. So you can imagine like a little chunk like this would be a little ds. And what we do is we start at the start of our curve, and then we travel along the length of the curve, and you can think that on every single one of these chunks, we're taking a little bit of f, and then we're going to add it up with f along all the other chunks until we reach the end. Add all that up together, and we get approximately the value of the integral. That'd be kind of like your Riemann sum argument about what a line integral is. So the thing is that line integrals will act like integrals you learned about in prior classes. So they're going to act like you expect any integral a to b f with respect to x. Because this is itself a 1D integral. This is very similar to integral from a to b f dx. It's more similar than the types of integrals we were working with previously. So what that means is you're going to have a bunch of properties that I'll go ahead and write out for you right now. So if you're taking the integral over some curve of a constant times a function, you can go ahead and pull that constant out front. If you are integrating the sum of two functions, you can break them up into two separate integrals. I know that these are not exciting properties. I promise the next two are a lot cooler. And then your bounds for line integrals can switch around the same way you expect bounds from 1D integrals to act. So just like you expect a to b f dx to equal negative b to a f dx, you're going to have a property for line integrals that says the integral of f ds is negative the integral of negative c f ds for negative c, the reverse of curve c. So in this picture, this was c. So negative c would just be one that starts here. Oh, I'll do it in a different color. Starts lighter color here, where this one ended, and kind of goes along the exact same path, if I was better at drawing, but travels this opposite direction. So it's just the reverse, switching direction. And if you switch direction on your integral, it just creates a negative sign. Just like if you switch the order a to b, you get a negative sign. And then just like you could take integral a to b plus integral b to c f dx, and it would be the same as integral a to c f dx. You're going to have that if you add two curves together and integrate separately, you get the same as if you integrate over the entire curve. So the example over here would be, instead of integrating over all of c, suppose I went ahead and I broke it up into, here's my integral, I don't know, stops there. There's my c1 heading in that direction, and then here's my c2 heading in that direction. And if I integrate over these two components of the curve separately, I'll get the same as if I integrated over the entire c that I drew to start. So, all that to say, pretty much everything you think is true about integrals is going to stay true about line integrals. And so, since I'm telling you that line integrals are really intuitive and similar to things you're used to, you probably wonder why we're covering it. And the reason is because solving line integrals is kind of tricky. And we're going to write out the steps, but I think we should probably cut this video off and then we'll pick up the next video with like the algorithm you can follow to solve this type of problem.